IPv6 SLAAC Overview. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, focusing on networking. Also, hit the bell icon to get notified of new videos. IPv6 Stateless Address Autoconfiguration, commonly abbreviated as SLAAC, represents one of the most significant innovations in IPv6 networking. Unlike IPv4, where hosts typically require manual configuration or a DHCP server to obtain IP addresses, SLAAC enables IPv6 hosts to automatically configure themselves with globally route-able addresses without any centralized server. This mechanism fundamentally changes how network addressing works, making IPv6 networks more scalable and easier to manage. The SLAAC process relies heavily on router advertisement messages, which are ICMPv6 messages sent periodically by routers or in response to router solicitation messages from hosts. These router advertisements contain critical information including the network prefix, prefix length, default gateway information, and various flags that control how hosts should configure their addresses. When a host receives an RA, it extracts the prefix information and combines it with a locally generated interface identifier to create a complete IPv6 address. The concept of the interface identifier is central to SLAAC. Originally, IPv6 standardized the EUI-64 format for generating interface identifiers, which derives a 64-bit identifier from the host's 48-bit MAC address. This approach provided a deterministic way to generate unique addresses and ensured that each network interface would have a predictable, consistent IPv6 address. However, this predictability also introduced privacy concerns, as the MAC address embedded in the IPv6 address could be used to track devices across networks. To address these privacy concerns, RFC 4941 introduced privacy extensions, also known as temporary addresses. These extensions generate randomized interface identifiers instead of using the MAC-based EUI-64 format, making it significantly harder to track devices across networks. Modern operating systems typically implement both mechanisms, using stable EUI-64 addresses for server functions and temporary addresses for outbound connections, providing a balance between stability and privacy. EUI-64 Address Formation. The EUI-64 address formation process is a mathematical transformation that converts a 48-bit MAC address into a 64-bit interface identifier suitable for use in an IPv6 address. Understanding this process requires examining both the structure of MAC addresses and the specific steps involved in the transformation. A MAC address consists of 6 octets, typically written in hexadecimal format separated by colons or hyphens, such as beginning with 00 and ending with 55. The first step in EUI-64 formation involves splitting the MAC address into 2 halves. The first 3 octets represent the organizationally unique identifier, assigned by the IEEE to manufacturers, while the last 3 octets are assigned by the manufacturer to individual devices. To convert this 48-bit value to 64 bits, we insert 2 specific octets, FF and FE, in the middle of the MAC address. This insertion happens between the 3rd and 4th octets, expanding the address from 6 octets to 8 octets. The second critical step involves flipping the 7th bit of the first octet, known as the universal or local bit, or UL bit. In the original MAC address, this bit indicates whether the address is globally unique or locally administered. When set to 0, the address is globally unique. When set to 1, it is locally administered. During EUI-64 formation, we flip this bit to indicate that the resulting identifier is derived from a globally unique MAC address. This bit flip is performed using an XOR operation with the value 0x2. Let's work through a concrete example to illustrate the complete process. Starting with the MAC address 00:11:22:33:44:55, we first split it into 2 parts. 00:11:22, and 33:44:55. Next, we insert FF:(FE) in the middle to get 00:11:22:FF:(FE):33:44:55. Then, we flip the 7th bit of the first octet. The first octet is 0x00, which in binary is 00000000. Flipping the 7th bit gives us 00000010, which is 0x02 in hexadecimal. The final EUI-64 identifier becomes 02:11:22:FF:(FE):33:44:55. Or, when written in IPv6 format as part of a complete address with a prefix of 2001:DB8:/64. The full address would be 2001:DB8:2211:22FF:(FE):33:44:55. The EUI-64 format provides several advantages in terms of address management and troubleshooting. Network administrators can easily identify which device is using which address by examining the interface identifier portion. If you see an address with FF:(FE) in the middle of the interface identifier, you know immediately that it was generated using EUI-64. Additionally, because the transformation is deterministic, the same network interface will always generate the same IPv6 address on the same subnet, which is useful for services that need consistent addressing. Privacy extensions and temporary addresses. Privacy extensions, formally specified in RFC 4941 and updated by RFC 8981, emerged from growing concerns about the privacy implications of EUI-64 addresses. When you use EUI-64 to generate IPv6 addresses, the MAC address is effectively embedded in every IPv6 address your device uses. This creates a persistent identifier that follows your device across different networks, allowing observers to correlate your activities and track your movements. If you connect to a coffee shop's Wi-Fi, then later connect to your workplace network, the same interface identifier appears in both locations, making it trivial to link these activities to the same physical device. The fundamental principle behind privacy extensions is the generation of randomized interface identifiers that change periodically. Instead of deriving the interface identifier from the MAC address, the operating system generates a cryptographically random 64-bit value to use as the interface identifier. This random value is combined with the network prefix from the router advertisement to form a complete IPv6 address, just like with EUI-64, but without any correlation to hardware identifiers. Modern implementations of privacy extensions maintain two types of addresses simultaneously on each interface. The stable address, generated using EUI-64, serves as the primary address for inbound connections and is used when the device acts as a server. The temporary address, generated randomly, is used for outbound connections and changes on a regular schedule. This dual address approach provides privacy for client activities while maintaining reachability for server functions. The typical lifetime for a temporary address is 24 hours, with new addresses generated before old ones expire to ensure continuous connectivity. The address selection algorithm, defined in RFC 6724, determines which address to use for each connection. When initiating an outbound connection to another IPv6 address, the host prefers to use a temporary address if one is available. When receiving inbound connections or responding to connection requests, the stable EUI-64 address is typically used. This intelligent selection happens automatically at the operating system level, requiring no application modifications. Applications simply request an IPv6 socket, and the operating system handles the complexity of choosing the appropriate source address based on the connection type and direction. Organizations implementing IPv6 need to carefully consider the implications of privacy extensions. In enterprise networks, administrators often need to identify which device is communicating on the network for security monitoring, troubleshooting, and policy enforcement. Privacy extensions make this identification more challenging because addresses change frequently and do not correlate to hardware identifiers. Some organizations choose to disable privacy extensions in their corporate networks while enabling them for guest or BYOD networks, striking a balance between privacy and management needs. The implementation details vary by operating system, with Windows, Linux, and Mac OS each offering different configuration options and defaults for privacy extensions. Duplicate Address Detection, DAD. Duplicate Address Detection, or DAD, serves as a critical safety mechanism in IPv6 autoconfiguration to ensure that each address configured on a link is unique. While the probability of address collisions in IPv6 is extremely low due to the vast address space, DAD provides absolute certainty that no two hosts on the same link will use the same address. This mechanism is mandatory for all unicast addresses, whether configured through SLAAC, DHCPv6, or manual configuration, making it a fundamental component of IPv6 address management. The DAD process utilizes ICMPv6 Neighbor Solicitation and Neighbor Advertisement messages, which are part of the Neighbor Discovery Protocol. When a host tentatively assigns an IPv6 address to an interface, it enters the address into a tentative state before making it fully operational. During this tentative state, the address is not yet usable for sending or receiving normal traffic, but it can be used specifically for DAD purposes. The host must verify that no other node on the link is already using this address before transitioning it to the preferred state where it can be used for communication. The verification process begins with the host sending a neighbor solicitation message to the solicited node multicast address corresponding to the tentative address. This multicast address is algorithmically derived from the last 24 bits of the IPv6 address, ensuring that only nodes with similar addresses need to process the message. The neighbor solicitation uses the unspecified address, which is represented by $:, as its source address. This is because the tentative address cannot yet be used as a source. The target address field, however, contains the tentative address being tested. If any node on the link is already using this address, it will respond with a neighbor advertisement message. RFC 4862, which defines SLAAC, specifies that a host must send at least one neighbor solicitation and wait for at least 1 second before considering the address unique. In practice, most implementations send multiple solicitations to increase reliability, typically sending one solicitation per second for a configurable number of seconds, usually 3. During this waiting period, the host monitors for any neighbor advertisement messages claiming the tentative address. If a response arrives, the DAD process fails, and the host must not use the address. The host then typically generates a new random interface identifier and repeats the entire DAD process with the new address. The consequences of DAD failure depend on how the address was generated. For EUI-64 addresses, a DAD failure is extremely serious because the address is derived deterministically from the MAC address. If DAD fails for an EUI-64 address, it typically indicates a misconfigured network, duplicate MAC addresses, which should never occur with genuine hardware, or a malicious device on the network. For privacy addresses, DAD failure is less concerning because the system can simply generate a new random identifier and try again. Modern operating systems implement exponential backoff mechanisms when DAD failures occur repeatedly, preventing denial of service scenarios where an attacker causes continuous DAD failures. Complete SLAAC process flow. The complete SLAAC process involves a carefully orchestrated sequence of steps that begins when a host's network interface becomes active and continues until the host has one or more fully configured IPv6 addresses. Understanding this complete flow is essential for network engineers troubleshooting IPv6 connectivity issues and for developers implementing IPv6 support in network applications. The process integrates router discovery, address generation, and duplicate address detection into a seamless autoconfiguration mechanism. The process begins with the host configuring its link local address, which is a mandatory first step in IPv6 networking. Every IPv6 interface must have a link local address, which uses the FE80:10 prefix and enables communication with other devices on the same physical link. The host generates this link local address using either EUI-64 or a random identifier, performs DAD on the link local address, and only proceeds with SLAAC after the link local address is confirmed unique. This link local address becomes the source address for all subsequent router solicitation messages. Once the link local address is operational, the host sends a router solicitation message to the all routers multicast address FF02:2, requesting that routers on the link immediately send router advertisement messages. Routers normally send RAs periodically, but the RS mechanism allows hosts to receive configuration information immediately when they join the network, rather than waiting for the next periodic advertisement. The router solicitation contains the host's link local address as the source, allowing routers to potentially optimize their response by unicasting the RA directly to the requesting host. When a router receives a router solicitation, or when its periodic RA timer expires, it sends a router advertisement message containing comprehensive network configuration information. The RA includes the network prefix and prefix length, typically a /64 subnet, which forms the first 64 bits of the global IPv6 address. The RA also contains the M, as in managed, and O, as in other, flags that indicate whether the host should use DHCPv6 for address assignment or other configuration parameters. Additionally, the RA includes router lifetime information, MTU settings, and potentially additional options, like DNS server addresses, through the RDNSS option specified in RFC 8106. Upon receiving the RA, the host extracts the prefix information and combines it with a locally generated interface identifier to form a tentative global IPv6 address. If privacy extensions are enabled, the host generates a random 64-bit interface identifier. Otherwise, it uses EUI-64 to derive the identifier from the MAC address. The host then performs DAD on this tentative address, sending neighbor solicitations to the solicited-node multicast address and waiting for responses. If DAD succeeds, the address transitions to the preferred state and becomes usable for communication. If privacy extensions are enabled, the host typically generates both a stable EUI-64 address and one or more temporary addresses, performing DAD on each one independently. The final configuration includes setting the default gateway to the link local address of the router that sent the RA, configuring the address lifetimes based on the preferred and valid lifetime values from the RA, and potentially configuring DNS servers if they were included in the RA. The host may configure multiple global addresses if it receives RAs from multiple routers or if it has multiple prefixes advertised. Throughout the lifetime of these addresses, the host monitors for updated RAs that might change the configuration, handles prefix deprecation when routers stop advertising certain prefixes, and regenerates privacy addresses before they expire to maintain continuous connectivity. Thank you for your attendance. Please consider subscribing to the channel and liking this video.